All right. I think that we are ready to commence today. Good morning, everybody. Welcome to the Ohio Stormwater Association webinar today. We are presenting on designing active construction sediment settling ponds this morning, and a quick preview on, we're using the Zoom platform. This session is going to be recorded. We do ask that if you would please make sure that your name in Zoom reflects the name you would like on your CEU certificates. And if you need some help on renaming yourself, you should be able to hover over your tile, if you will, and a little 3 dots appears, and you should be able to click on that and select rename from there. So please make sure you rename yourself so that your full name shows on your Zoom screen and appears the way you want it to appear on your CEU certificate. OSWA is dedicated to advancing the management of stormwater and related natural resources through education, leadership, watershed-based coordination, and technical assistance in Ohio. That is our mission and vision statement, and I am on the board of directors for Ohio Stormwater Association and have been doing that for the past several years, I think maybe 3 or 4 now. We are a nonprofit organization, non-political, and we are part of WAMO. So we do have a board of directors and additional board members that if you ever have any questions about Ohio Stormwater Association, please reach out to any one of us. We'd be more than happy to share more information. To join the Ohio Stormwater Association, you do that through WAMO. And when you are joining WAMO, you want to check the box that's circled here in red that says stormwater, and then you will be part of the part of our division of WAMO with the Ohio Stormwater Association. We do have several several subcommittees within the Ohio Stormwater Association that works towards a variety of different things: education, marketing and membership, regulatory, and transportation subcommittees. So there are opportunities for folks to volunteer with the Ohio Stormwater Association. Even if you are not specifically on our board, we do have additional volunteers who help us do a variety of things. Today, we are welcoming Wesley with the Ohio Environmental Protection Agency. He is located out of the central office and works for the Division of Surface Water. Wesley is a stormwater on the Stormwater Technical Assistance Team with Ohio EPA. He graduated from Cornell in 2019 with his BS in Environmental Engineering. He currently is an EIT working towards his PE status, I'm sure. He's also currently pursuing a master's degree from The Ohio State University. So welcome, Wesley, and I will let you take it from here. Please note, we do have some opportunity at the end for question and answer, and I believe, Wesley, you have some periods built into the talk where there might be some opportunity for Q&A as well throughout to give us a little bit of a break throughout the next hour. But we will have an opportunity for a full Q&A at the end of the session too. So can you take it over from here, Wesley?
That's correct. Thank you very much. All right. Well, to echo Anna's statements, thank you very much for attending this webinar. Today, I'm going to be presenting on sediment settling ponds, focusing mainly on sediment basins. This webinar is going to explore the technical design requirements and the guidance that exists for sediment settling ponds. Key points will include proper skimmer sizing, how skimmer outlet inverts control the size of the dewatering zone, length to width ratio requirements from inlet to outlet, and a few other common compliance and plan review issues. Additionally, I'll spend some time on the new Ohio EPA guidance and tools that include the recently released Q&A fact sheet and the sediment basin compliance spreadsheet. So a quick plug, as Anna mentioned, this presentation is a product of the Ohio EPA's Stormwater Technical Assistance Team, which is comprised of myself and my colleague Justin Reinhardt. He's also online today, helping to field questions as they come in. Our contact information is shown, and I encourage you to reach out and ask questions regarding the technical and design sides of stormwater. We're experts on the Rainwater and Land Development Manual, post-construction requirements, and stormwater pollution prevention plans. Well, without any further ado, let's jump right in. We'll start with the most basic question. What is a sediment basin? Succinctly put, it's a large, temporary settling pond used during active construction. It detains runoff and releases it slowly, no faster than 48 hours, from the surface via a skimmer. This allows most of the sediment particles to settle to the bottom, and then the cleanest water at the surface will be discharged. Key identifiers include what you can see in the picture: a permanent pool of water called the sediment storage zone, an outlet structure, here is a concrete outlet structure with a grate, and a skimmer device that will slowly draw down the runoff stored in the pond after a rain event, which is called the dewatering storage zone. Now that we've refreshed your memory on what a sediment basin is, let's talk about when they are used. The Ohio EPA's Construction General Permit outlines the conditions for which a sediment basin is required in Part 3, G2D of the permit. Anytime there is concentrated or collected stormwater runoff, like in a storm sewer or surface ditch, a sediment basin is needed. Additionally, when runoff from a drainage area exceeds the design capacity of sediment barriers, like silt fence, or any inlet protection BMPs, a sediment basin should be installed. To specifically address the when part, a sediment basin needs to be installed and fully functioning within 7 calendar days from the start of grubbing, which is the removal of roots and other soil embedded features after basic clearing has occurred. The basin needs to stay in use and be maintained until the site is permanently stabilized and has transitioned to post-construction. Essentially, unless your site is small, roughly less than 4 acres, and flat, sheet flow will concentrate beyond what silt fence and inlet protection can handle, which means the site will need a sediment basin. There have been a number of common questions that pertain to just these basic requirements. So a sediment settling pond fact sheet in Q&A style was developed to help provide some more clarification. We'll start to go through the questions from the fact sheet, but quickly I want to say that I'll show you exactly how to access this guidance document later in the presentation. Anyway, the first common question that is answered is whether or not a sediment settling pond is required to be installed. The short answer is no, but almost all developments end up needing a sediment basin or trap. We refer to basins as traps, basins and traps as the two types of sediment ponds used in Ohio. This table is taken right out of the permit, and it shows the maximum drainage area a sediment barrier, such as silt fence or compost filter socks, can effectively manage based on the slope of the contributing drainage area. Essentially, the steeper the slope, the smaller the area allowed. This drainage area limitation is the most frequent cause for a sediment basin to be required, but we always strongly recommend the use of ponds because of their durability compared to sediment barriers. The natural follow-up question to the first is, when can a sediment trap be used instead of a basin? Well, basins and traps are very similar, as both have the same volumetric requirements, but traps have a simple outlet structure made of riprap, while a basin has a defined outlet structure, usually made of concrete or a riser pipe, and has a skimmer attached to it. Traps are considered to be more temporary than sediment basins and should only be used when the drainage area is less than 5 acres and when the pond will not be converted to a post-construction basin in the future. Sediment basins are more effective than traps, so we encourage their use more strongly. Next, when should the sediment basin be built? Well, we already covered when they need to be installed prior to grading and 7 days before grubbing, but the point I will emphasize here is that a sediment basin is not built until it is 100% functional. So in the picture, the basin has been excavated and the site may be graded such that runoff is directed into the basin. But until the outlet structure and skimmer are in place, the basin is not functioning and in violation of the CGP. Without every piece in place, the basin won't provide treatment and is hardly better than a big hole in the ground. Working quickly to get the basin up and running properly will result in better treatment of stormwater runoff and improved water quality downstream. Sometimes questions come in whether or not a skimmer is required for a pond. Well, remember, sediment traps are dewatered through a simple riprap outlet, so they don't need a skimmer, but the CGP directly requires that a basin be dewatered from the surface. And to date, skimmer devices are by far the best method to accomplish that. The next phase of the sediment pond Q&A fact sheet begins to address sediment ponds and their relation to post-construction basins. The nomenclature adopted by the Ohio EPA for a post-construction basin is extended detention basin, and it applies to both wet and dry versions. Extended detention basins are permanent post-construction water quality control BMPs, which differs from the temporary active construction sediment control BMP that is a sediment detention basin. Now, understanding how the two practices differ, the obvious next question is, can an extended detention basin be used as a sediment basin? Yes, it's very common, but at a minimum, the outlet structure must be reconfigured when adapting a sediment basin to an extended detention basin at the end of construction. Chiefly because a sediment basin is sized to drain the dewatering volume, while extended detention basins are sized to drain the water quality volume. The sediment basin shown looks like it's just about ready to be converted to its post-construction state, in which the skimmer and riser will likely be removed and the water quality orifice installed. In the event that a sediment basin will be used as a post-construction extended detention basin, designated the specific time of when that transition should occur is very important. As mentioned earlier, sediment basins must stay in effect until the entire site is fully and permanently stabilized. Therefore, converting a sediment basin is likely one of the last steps in the construction sequence and can include a list of to-do steps. For example, regrading may be needed to add a forebay and micropool, or excavation to remove accumulated sediment. The storm sewers may need flushing, and sometimes as-built surveys need to be produced, depending on the local MS4's requirements. The next questions explain how a sediment pond should be implemented when other post-construction stormwater practices are planned to be used. If the post-construction stormwater control measure will be a bioretention or an infiltration basin, then it is advised to avoid using the same area for both. This is because a sediment basin is designed to accumulate sediment, which can clog soil pores and lead to reduced infiltration capacity in the long term. If it's not possible to avoid having the sediment basin and bioretention or infiltration basin in the same area, then it is recommended to leave at least 12 inches of undisturbed soil between the bottom of the sediment basin and the future bottom of the post-construction basin. Essentially, plan the sediment basin to be shallower than the post-construction practice by under-excavating. Then, when converting, fully excavate the basin down to its final grade, which will protect the infiltrative capability of the area. Another post-construction practice to discuss are underground systems, where there can be infiltrating or extended detention underground systems. For infiltrating systems, it is recommended to use the open excavation pit as the sediment basin, and then follow the under excavation guidelines mentioned previously, then install the underground system after the site has been fully stabilized. For extended detention underground systems, you can ignore the under excavation method, but do still use the open excavation pit as the sediment basin before installing the underground practice. It's very rare for underground systems to be used as sediment basins successfully, because the ability to fully extract deposited construction sediment from gravel void storage or geotextile fabrics prior to conversion to a post-construction control is just not practical. So as promised, we've come to our first short break, a pause for questions. So I'll see if Justin has any questions that I can answer at the moment.
Okay, Wesley, there was one that was typed into the chat. And it is, what, if any, options are available if site conditions prevent the construction or surface flow to a sediment basin, such as if the entire site is being developed and the post-construction detention is completely within a subgrade underground detention system or bioretention practice?
Great question. So that would be a situation where when that excavation pit is being dug for the underground system, that we would like the sediment basin to go in there. But like was asked in the question, if that area is going to be developed, there's going to be a parking lot or some sort of structure over top of it, that can pose a challenge. So what we would recommend there is to phase work as best as you can, to phase the project such that you can avoid construction over that sediment basin and what will be the underground system until the rest of the facility has been stabilized. And then that kind of eliminates the need for a sediment basin and can kind of help alleviate that problem.
Okay, Wesley, really quickly, one other question that came in.
Yeah.
If multi-basins are being used in a subdivision, and the area using one basin is developed and with yards stabilized, can one basin be converted, presumably to post-construction?
Right, so it's all a function of the drainage area. So once the drainage area is stabilized, then that basin is ready to be converted to post-construction. Now, what I wonder if this question might be getting at is when there are multiple basins in series, and that would be a case where you can have a large sprawling subdivision with many basins that lead into one another. What we would ask is that the downstream basin, the basin right before the ultimate discharge point, would be sized, would be fitted for a skimmer. We know that most of the sediment is going to be settling out in those upstream basins. So you can always use a skimmer up there as well, but ultimately we'll need a skimmer before we discharge to the receiving stream or the MS4. Well, thanks for those questions, Justin. I appreciate it. And we'll continue on to the next slide. So we've covered some of the crucial common questions regarding sediment basins. So now we can jump back into the design, starting by looking at the sizing of sediment basins. As mentioned before, the sediment storage zone is the permanent pool of water, and the dewatering zone is the runoff volume that is detained and drained slowly via the skimmer. Each zone has a specific volumetric requirement that is optimized to capture sediment. The dewatering zone is set at 67 cubic yards, or 1,800 cubic feet, per acre of total drainage area. The sediment storage zone, on the other hand, is set at 37 cubic yards, or 1,000 cubic feet, per acre of disturbed drainage area. Be sure to pay attention to that total versus disturbed drainage area, as that is frequently missed in sediment basin design. Geometry also plays an important role in the effectiveness of a sediment basin. It's required that a 2-to-1 length to width ratio for flow path is met, while a 4 or more to 1 is recommended. This measurement is taken by looking at the distance between the inlet and the outlet and comparing it to the average width of the basin along that path. Remember, the capacity and geometry requirements also apply to sediment traps, so don't go looking for different requirements when sizing traps. It's worth taking a little bit of time to discuss the sediment settling process, as it's the core function of sediment basins. When sediment-laden runoff enters the sediment basin, settling will immediately begin to take place. Larger particles like sand have a relatively high settling velocity and will drop to the bottom of the basin much more quickly than the fine particles like clay will. These fine particles can take a long time to settle out, so extending the hydraulic residence time, which is the average length of time water stays in the basin, as much as possible results in more settling and thus improved water quality in the discharge. Hydraulic residence time can be extended by increasing the flow path and eliminating short circuiting. So let's take a look at that visually on the next slide. These graphics shown give us a better understanding of how pool shape affects the sediment settling process and thus the effectiveness of sediment basins. I mentioned on the previous slide how shorter flow path and short circuiting negatively impact treatment, which is what the first set of graphics depict. On the left, the inlet is right next to the outlet. So the dirtiest runoff, shown in dark brown, will exit quickly and kind of short circuits the basin. So little settling is going to occur for most of that runoff. That basin design doesn't effectively utilize the entire basin, as the left half gets left out, because runoff isn't forced to travel through the whole basin. So the only spreading that occurs is because of dispersion. On the right, when the inlet is placed opposite of the outlet, runoff is forced to travel through the entire basin, which eliminates that short circuiting. The heaviest sediment is going to settle out right near the inlet. The next set in the middle of graphics depict how basin depth affects settling. For the same size basins, i.e. the same volume, the left basin has a relatively shorter flow path because it's deeper and has a smaller footprint, while the right basin is shallower and stretches that flow path out, which is better. The optimum dewatering depth is 3 foot and the maximum is 5 foot to ensure that basins can't be overly deep relative to their surface area. Lastly, the bottom two graphics revisit the length to width ratios. So you could see how a circular basin would be less effective because its flow path is shorter compared to its average flow width. You could perform a simple eye test by drawing a red line between the inlet and the outlet at the elevation that corresponds to the top of the sediment storage zone, then drawing a blue line perpendicular at the widest point along the red line. If the red line is at least twice as long as the blue line, like it is in the right basin, then you're good to go. When there are multiple inlets, though, you should take the average of each length to width ratio to see if the entire basin meets the requirements. Now we understand why basin depth and the volumetric capacity is important to sediment basin success, but we need to talk about what sets those volumes and depths. Ultimately, the outlet inverts dictate the volume provided in each zone of the basin. The invert at which the skimmer outlets controls the normal water elevation in the permanent pool, which sets the ceiling for the sediment storage zone and the floor for the dewatering zone. In the photo and in the diagram, the skimmer outlet is set right at or near the bottom of the basin, and that means little to no permanent pool can form, and also puts the skimmer at risk of getting stuck or buried in the mud. That's why it's so important to check what invert elevation the skimmer outlet's at. Problems can happen when there's a mistake during installation or during design, but if the rest of the basin is constructed and designed properly, luckily there might be an easy fix. Installing a stone pad for the skimmers to rest on can prevent them from dropping into the sediment storage zone and draining more than they should be. See how in the diagram at the bottom, the stone pad corrects that issue, and it provides each distinct zone without needing to change the outlet structure. This capture here depicts the important steps a contractor must take when installing the outlet structure. The notes in the green box explains that the skimmer needs to have an outlet hole, and it needs to be drilled, and then after construction ends, it must be sealed up for post-construction use. Notes like these are very, very helpful to the contractor, inspector, and especially the reviewer, as they show that the designer is thinking critically. A commonly missed instruction for sediment basins is to ensure that the water quality orifice is plugged or not installed until conversion to post-construction. So try to add that whenever possible. Whenever possible, sediment basin drawings should reflect the actual design and outlet structure and should include important invert elevations, dimensions, and specific instructions like this. While it may be easier to use a generic outlet structure drawing, it can result in misunderstandings. When detailed drawings and instructions don't exist, and it leads to mistakes, problems can quickly arise. Outlet structures that serve during both active and post-construction need to be designed with both phases in mind, and detailed notes should accompany them in the SWIP to ensure that the proper storage volumes are provided. For example, the top photo shows an outlet structure that has attempted to plug the secondary outlet with geotextile and scrap wood. This is not going to provide the watertight seal that the plans may require to achieve the necessary sediment or dewatering storage zones. Another issue is the skimmer connection. Hastily assembled connections can break and result in a basin that dewaters from the bottom, not from the top. Following the skimmer manufacturer's guidance is the best method to achieving success, but be sure that the method specified will work with the outlet design of the basin. It can be confusing for contractors to install the outlets if plans are vague. There can be multiple invert elevations depending on the basin, and then they can change from active to post-construction. Well-designed outlet structures avoid the need for temporary orifices and plugging. But if that is unavoidable, clear plan notes can make a huge difference in the success of the basin. But right now, let's look at the edges of a sediment basin, specifically its banks. It's all too common for banks to be left unstabilized. Designers or contractors may think, well, what's the use? The whole point of the basin is to collect sediment, so why bother seeding and mulching the banks? Well, first, the CGP's temporary stabilization requirements also apply to the banks of sediment basins, so the site wouldn't be in compliance. Secondly, that short-sighted viewpoint overlooks the stabilization of sediment banks can actually end up saving money and benefiting water quality. When left unstabilized, banks erode in on themselves, which will require more work in the future to fix. Additionally, the basin's sediment storage will fill up more quickly and can even overwhelm the skimmer in some cases. The graphic above shows a basin where erosion has filled up the basin and now hardly any permanent pool remains. The sediment storage zone is an important piece in the sediment settling process, and when it is significantly impaired like this, it results in muddier and muddier runoff being discharged, harming water quality downstream. On top of this, the sediment storage zone is supposed to be emptied when the volume has been reduced by 40%, which in some cases may mean mucking out the sediment basin more than once during the active construction phase, a process that could be expensive and could have been avoided with better stabilization. But how do you measure that 40% for when a basin needs to be cleaned out? Typically, sediment accumulation in the permanent pool is monitored through the use of multicolored stakes that indicate depths. For example, in the graphic, a stake painted red and green could be used to show where that 40% elevation is in relation to the top of the sediment storage zone. Including a few of these stakes positioned around the basin, especially near the inlets and outlets, can help make that determination easier because sediment isn't going to settle out uniformly. The bulk of it will occur near the inlets, so using an average depth is an acceptable method of monitoring sediment accumulation. Of course, you're not going to be able to see anything right after a precipitation event because of cloudy water, so timing your inspections is crucial. It's a good practice to include a clear procedure in the SWIP, which states how to tell when cleanout should occur, such as stakes that mark a certain elevation in the basin and how to read them, and how often regular cleanout should occur. Additionally, the removal and disposal process for that dredged sediment must be included. We've reached another short break point, so I'll see if Justin has any more questions for us.
Okay, Wesley, quite a few questions coming in here. I'm trying to sort through them and a little bit out of order. And we will try and get to all the questions at some point. A question that's come up in several forms has been regarding residential subdivisions with the possibility of having vacant lots over a period of time, and when it is appropriate to convert sediment pond to post-construction.
Right, and so that all comes down to the stabilization. So if there are some vacant lots that haven't been built out yet, the best recommendation is to work on temporary stabilization. And we do have those temporary stabilization requirements, 7 days. They need to be stabilized in some fashion within 7 days if they're going to be left as is. So if a home isn't going to be built in those vacant lots, then they do need to be temporarily stabilized. And then that would mean that you could convert the basin to post-construction once that stabilization occurs. Now, a lot of it is a factor of what percentage of the overall site, and that tends to be more of a judgment call. If the vast majority of the site, more than 90%, has been built out and is fully stabilized, then maybe that's a time where individual lot controls or inlet protection and sediment barriers can be an effective means to control sediment and erosion, as opposed to needing a skimmer and a sediment basin. I hope that answered the question. Do you want to see if we've got one more?
Hey,
Before I move
if
on?
you have time,
Yeah.
You could, I'm gonna save some of these towards the end and let you keep going. I
Okay.
think.
Okay. Well, then I will keep right on going. Our next slide gets into the sediment basin compliance spreadsheet. One way to help the reviewer, but it also can be a great tool for engineers and consultants, is to integrate the sediment basin compliance spreadsheet into your repertoire. This spreadsheet is very similar to the BMP compliance spreadsheet, but if this is new to you, don't worry. A detailed walkthrough will be made available later this spring, but for now, I'll address the important takeaways and the tidbits. Also, I'll discuss later how to access the sheet, but let's imagine you just opened up the spreadsheet. There are 3 tabs you're going to see: Introduction, Basin Sizing and Dewatering Tool, and Regulatory Guidance. The Introduction tab provides some background and instructions and has a reminder that the spreadsheet was primarily designed as a compliance check tool to aid designers and reviewers, not really as a complete design tool. So it does not account for local peak discharge or flood control regulations. The Regulatory Guidance tab at the end contains a table summary of all the numeric requirements specific to sediment basins. So it could be useful to use that as a mental check to make sure the major design conditions have been met. For the middle tab, we advise that a separate basin sizing and dewatering tool tab be filled out for each sediment basin, and that this completed tab be included in the SWIP along with a basin spec sheet, a drainage area map, and any other documentation that may aid in the review and construction process. Lastly, to head off any thoughts, the Ohio EPA does not evaluate, approve, or maintain a list of any approved proprietary products, which includes skimmers. Thus, the inclusion of the skimmers referenced in this spreadsheet is not an endorsement of these products. Lastly, if anything in the spreadsheet appears to be amiss, or if you have questions, feel free to reach out to me for assistance. The basin sizing and dewatering tool tab is really where all the action happens, and the central part of it is filling out the project summary fully. I cannot stress enough the importance of correctly selecting the watershed and entering the accurate total and disturbed drainage area for the basin. The rest of the spreadsheet builds upon these entries, so double check to make sure you're working in the selected watershed and that you've calculated the drainage areas properly. Remember, drainage area is a product of the land features and only follows slope, not project boundaries. So check for offsite drainage area. Also, the Big Darby Creek has different volumetric requirements than the rest of the state, and it results in specifically a doubling of the required dewatering volume. And that is sometimes missed by design engineers who aren't familiar with that watershed. Your eyes may be drawn to the basin schematic that helps visualize the information provided in the stage storage table in step 2 or the outlet elevations in step 3, but the key pieces to focus on are those green input cells. It's vitally important that the exact skimmer outlet or stop elevations and the secondary outlet elevations are provided in the stage storage tables of step 2 with their corresponding drainage areas. Those elevations must match the elevations provided in step 3. If not, the spreadsheet is not able to compute the provided volumes. And then if those compliance check cells display an NA or a not okay message, read through the guidance text to the right of the cell to see what might be the matter. For example, a not okay message for the secondary outlet invert elevation may mean that the depth of the dewatering zone exceeds 5 feet. Step 4 of the spreadsheet is the skimmer selection and sizing process. First, select the drawdown from the drop down which skimmer will be used. The options are going to be listed in alphabetical order. If the Delaware DOT skimmer is selected, then a built-in calculator will appear below. However, if another option is selected, like the ESC, Bearcloth, or Marley Float skimmers, then the spreadsheet is going to direct the user to the calculator provided by that manufacturer via a hyperlink. Be sure to check whether you are inputting the required versus provided dewatering volume when using those online manufacturer calculators, because some of them suggest you should use provided when you really should be using required. I'll explain this important distinction after going through the compliance spreadsheet fully. And lastly, input the orifice diameter size, which is different than the skimmer size. For example, if the calculator requires that a 4-inch X brand skimmer with a 3.2-inch diameter orifice is needed to drain the dewatering volume in more than 48 hours, please provide the 3.2-inch diameter orifice, because that is the restricting control orifice, not the 4-inch skimmer pipe. But before I continue through the rest of the spreadsheet, this would be a good time to address the last question that I haven't covered from the sediment basin Q&A fact sheet. After selecting the skimmer type from the dropdown, it may make you wonder if the size and type of skimmer really matter. Well, yes and no. Any type, model, or brand of skimmer device may be used. However, the skimmer usually includes a flow limiting orifice, which must be properly sized to meet that minimum 48-hour drawdown of the required dewatering volume, and it can't exceed 7 days either. Some sizing guidance is provided in the Rainwater and Land Development Manual, but it's mainly for the Delaware DOT skimmer. So proprietary skimmers should be sized according to the manufacturer's recommendations and then be checked against the CGP requirements. Each skimmer is going to dewater a little differently, so plans must specify which skimmer type and size the design intended. A Faircloth skimmer cannot just be swapped for an IAS or Marley Float skimmer without first checking the design calculations to see if any sizing changes are needed. Our inspectors have noted that it's all too frequent to see the plans specify a certain size and brand skimmer in the SWIP, only to find a totally different skimmer installed on site, which is not permissible. Jumping back into the compliance spreadsheet, after selecting skimmer type, the displayed boxes will appear. The capture I'm showing here is unique to the Delaware DOT skimmer, as it's the only option that has a built-in sizing calculator. The calculation method is done using the variable head method, meaning the constricting orifice is located in the end of the skimmer pipe at the outlet instead of in the head of the skimmer. And this is all described in the skimmer sizing section in the sediment basin chapter of the RLD. As I said, other skimmer types do not have a built-in calculator, so you're instead going to have to go to the manufacturer's guidance or calculator and do the sizing there. Remember, the drop-down will present a link that'll take you right to those tools for each manufacturer. It is recommended that a screenshot of that calculator be included in the SWIP as proof that the size selected will result in the desired drawdown. Also, for each skimmer type, there's a detailed drawing or spec sheet that can be copied right into your SWIP, and a photo that's just for reference to what the skimmer is going to look like in the field. As I mentioned before, some skimmer manufacturers' guidance suggests that the provided dewatering volume be used when sizing their skimmer. This results in a common compliance issue that's caught during thorough plan reviews and offers a good opportunity for a small case study of sediment basin sizing, or more specifically, the skimmer sizing process. The focused question is, which dewatering volume do you use when sizing your skimmer? Required or the provided? The short answer is required. This is frequently missed and misunderstood. And depending on the skimmer selected, as I said, the manufacturer's guidance may compound this confusion, as some proprietary guidance directly conflicts this. However, my aim is to explain why the Ohio EPA asks for required over provided. With dual use basins, the ones that serve during active and post-construction, the sediment basin side is often graded to store larger post-construction volumes. Thus, it's common for a sediment basin to provide significantly more volume than is required, as it minimizes the excavation needed to transition from sediment basin to post-construction basin. When using the larger than required dewatering volume, it leads to oversizing of the skimmer, which is then going to decrease the water quality of the discharge for most storms. The following example will help to explain this problem with oversizing in a little more detail. So our example looks at a 10-acre site that's going to need a sediment basin. Two different designs are proposed. The first, design A, meets the bare minimum requirements of 1,800 cubic feet of dewatering volume per acre times 10 acres equals 18,000 cubic feet. And for the sake of the example, we'll use the Faircloth skimmer, though not to pick on them. Using Faircloth sizing calculator on the website to meet the 48-hour minimum drain time, a 3-inch skimmer with a 2.9-inch diameter orifice plate is needed. The second design, B, chooses to make the sediment basin big enough that it will need little earthwork to transition into post-construction, likely only needing the skimmer to be removed and the orifice sealed up. And it holds 54,000 cubic feet of dewatering volume. Following the guidance on Faircloth's website directly, which reads, volume is the actual or provided volume you intend to drain, usually not the required volume, which is often smaller. It would suggest a 5-inch skimmer with a 4.6-inch diameter orifice plate is needed to drain that 54,000 cubic feet in 48 hours. Therefore, the basin is 3 times larger than the one from design A, but both designs are for the same drainage area. So this is really where we start to see why this is such a problem. So if we imagined a rain event that yielded a 1/2 inch of runoff, basin A would fill the dewatering volume completely, and then it would drain in 48 hours, just as designed. However, basin B would only fill 1/3 of the dewatering volume provided. And because the skimmer is so much larger, it's going to take less than 24 hours for the volume to drain. Therefore, per the requirements of the CGP, basin B is not treating the required volume appropriately. This is why, despite the larger provided volume, basin B must have an orifice sized on the required dewatering volume, not provided. Now, I will say that the Ohio EPA acknowledges that Basin B would have the potential to detain runoff from larger storm events, but as event size grows, their frequency decreases. So a larger basin that can detain and treat larger events is going to fail to treat smaller and more frequent storms effectively. This explains why the CGP requirements are defined as they are, which is focused on successfully treating the most frequent storms. You're still more than welcome to provide the increased dewatering volume. Just remember to size the skimmer on the required volume, not provided. And with so many different components that need to go into a SWIP, it's easy for things to get disorganized or become confusing. The plan review process can sometimes end up being an exercise in deciphering or hunting for pieces of crucial information. It's highly recommended that engineers include a summary table, like the one shown here, to help bring all of those different pieces together in one place. You'll still need to provide the calculations and explanations, but a table like this makes the review process better for everyone involved. Packaging up the sediment basin and post-construction basin information side by side gives a quick and easy way to see if the project has accounted for the important components of basin design and permit requirements. Any opportunity to make the review process more streamlined is one worth pursuing, as it will speed up your review process and get your project up and going more quickly. We have covered a vast array of material today, so it's time to put what we learned to the test. Let's pick out the qualities that make a sediment basin great, starting with how water is going to enter the basin. We see that the inlet has rock protection for energy dissipation and erosion control, and then is going to direct that water into a forebay. A forebay isn't required for sediment basins like it is for post-construction dry extended detention basins, but they are encouraged because they improve settling and concentrate that accumulated sediment for ease of removal. For any runoff that enters the basin via sheet flow, the banks are either well stabilized with a thick stand of grass or is covered with erosion control matting, both of which are going to slow down runoff, encourage infiltration, improve settling, and reduce bank erosion. We can see that the inlet is located on the opposite end of the basin from the outlet, maximizing that flow path length. And we can see that the shape of the basin meets the 2-to-1 length to width ratio requirement. Added into that is a set of porous core baffles that impede flow as to reduce short circuiting and will increase that important hydraulic residence time. We can also see a skimmer back there attached to the outlet structure that is drawing water from the surface. And there's also a stone pad included in the plans that is going to ensure a permanent pool of water is maintained for sediment storage. Altogether, this looks like an excellent sediment basin that would be very effective, easy for a reviewer to approve, and easy to maintain. Just like I need to make sure that I covered all my intended topics today, we can do a design check to make sure that you have all of your bases covered too. First, does your design include a sediment storage zone sized at 1,000 cubic feet per acre of disturbed drainage area? Does this permanent pool have a method to indicate when it is filling up with sediment and may need to be cleaned out? Is the permanent pool safe from being drained by the skimmer via outlet invert elevation control or a provided stone pad? Hopefully, those are all checks, and you can assess whether or not the banks of the basin are set to be stabilized or reinforced in some manner to control erosion. If so, does the sediment basin have a dedicated outlet structure with clear and easy to follow instructions for installation to ensure proper function during both active and post-construction? And has a method been proposed to firmly affix that skimmer to the outlet pipe? You wouldn't want to go to all of this excellent work only for confusion to trip up an otherwise successful design right at the last moment. Next, check that the flow path length to width ratios are at least 2-to-1, and consider if internal baffles or dikes can be used to lengthen that hydraulic residence time. If flow path is acceptable, the dewatering volume needs to be properly sized at 1,800 cubic feet per total acre of drainage, or 3,600 cubic feet if your project happens to sit in the Big Darby Creek watershed. It also must be less than 5 feet deep to help promote the best settling you can get. With the watering volume set, the skimmer is the next focus area to review. Has the skimmer been sized on the required dewatering volume, and is it set to drain in no less than 48 hours? Luckily, you can do most of these checks by filling out the sediment basin compliance spreadsheet and including it in your SWIP, something that your reviewer will likely thank you for. However, if any of these checks don't result in a pass, there are always steps that can be taken to improve sediment basin design and performance. Now you've got a whole extra set of tools in your sediment basin design toolbox that you can use to employ to address issues. But don't hesitate to reach out or look for more guidance to help you take the right steps. And speaking of guidance, I promised earlier to provide a roadmap to accessing all that is available. So here it is. Step one is going to be to navigate to the Ohio EPA Stormwater Program webpage. And that can be done by going to epa.ohio.gov/DSW/storm/index, or just by searching Ohio EPA Stormwater Program online. Once on the page, you'll need to scroll down until you can see the tabs. For today's materials, you'd select construction activities, but if you wanted to access industrial or MS4 guidance, you could select those tabs instead. Clicking construction activities presents a set of 5 drop-downs. Technical assistance and permit compliance materials is where most of the guidance documents are contained, but if you're interested in the unique conditions of the Olentangy or the Big Darby Creek watersheds, you could select those drop-downs for more specific information. Each tab is broken down into sections, and the first you're going to come across is the Stormwater Design Manuals tab, and that's home of the Rainwater and Land Development Manual. In there, you're going to find Chapter 6, Sediment Controls, which contains subchapters on sediment basins and sediment traps. Technical memos that provide updates to the manual are also going to be kept on that page. After design manuals comes the erosion and sediment control Q&A documents, the home of the sediment pond fact sheet we went through today. And then there are more post-construction Q&A documents that follow below that. After all that are the tools and spreadsheet section, with the home of the sediment basin compliance spreadsheet. And then other guidance documents are provided farther down, like fact sheets on meeting post-construction requirements for renewable energy facilities, like wind turbine or solar panel array developments. And I highly encourage you to explore the page and find the various documents put out to help improve everyone's understanding. So that brings me to the end of my presentation. I want to thank you all very much for your attention. Here's a pretty nice summary slide that helps figure out who you should contact given your question in the Ohio EPA Stormwater Program. So I'll sit here and hopefully field some more questions that you sent in during the presentation.
Okay, Wesley. A couple of questions have come up here regarding the length to width ratio, and that might be something to address. One specific question regarding length to width ratio. I've always used the guidance to calculate width as surface area divided by L, or length, where L or length is the straight distance between the inlet and outlet. If not using curtains or baffles, is that still a valid method for irregularly shaped ponds?
Yes, that can be an effective tool to measure that length to width ratio, but you also have to remember to kind of do that eye check to see, is there any way that you can stretch those inlets and outlets so that they're farther apart or on opposite ends of the basin. So the eye test in combination with that method described would be acceptable.
Okay, just a couple of questions here that are non-technical, but being asked if the slides will be shared after the presentation. Oh, and Teresa's answered that. Okay.
Oh, go ahead.
Okay,
Teresa.
that there will be a recording available.
Yes,
made
that
available.
too.
Okay, question here on infiltration basins, and I'm not certain the direction of this, but are infiltration basins used in place of sediment basins? And if so, are there compliance worksheets available via Ohio EPA?
So not really. An infiltration basin is one of those post-construction practices. And so it's, as I mentioned, an infiltration basin works by allowing water to infiltrate into the ground. And a sediment basin works by collecting sediment and settling it on the bottom of the basin, usually collecting a layer of clay or other sediment that is going to impede that flow. And so you've got two different basins there that are directly conflicting. So an infiltration basin can't be used as a sediment settling pond during active construction. And so that's why we have that guidance to do that under excavation method to help protect the infiltrative capability of the soil underneath that bottom of the sediment basin.
Yes, an infiltration basin is generally post-construction practice, so a little bit of apples and oranges there.
Exactly.
Another question, what is the current basis of design, RE, the volumetric or flow rate, a 50-year, 100-year flood event or other, etc.?
Right, so that has to do, we employ the critical storm method, but really those requirements break down, are broken down at the local level. So we don't really regulate those large storm events at the 50 or 100-year intervals from a state level.
Yes, and from the sediment basin side of things, we're looking at generally a, if I'm not mistaken, a ½ inch of rain falling over the drainage area as far as the sizing basis goes.
Exactly. That's where that 1,800 cubic feet of storage comes from. If you do unit conversion, that correlates to a ½ inch of depth over an acre. So it's a ½ inch acre. Acre inch, yeah.
Okay, another question that just came in, are there any detention practices available for brand new culverts in a jurisdictional stream that can be placed within a stream? Parentheses, flow was once spread out over land, is now being concentrated through a new culvert.
That is a good question. So when it comes to streams, we do not permit that any permanent post-constructive or active construction practice be placed within the stream. We really want to see those things separated because the stream is going to provide a lot of additional benefits that a sediment basin or a post-construction basin just really can't provide. So we would work to try and find as many opportunities as possible to move those BMPs out of the stream area. And I know that sometimes that can be difficult, but it takes some creative design thinking to come to a solution.
Okay, there are a number of questions that were sent directly to me. Some of them are not necessarily related to sediment controls, and I'm happy to address those individually as perhaps after the presentation. And feel free to email those or other questions.
Of course, yeah, always feel free to reach out to Justin or I. You can see our emails there in the top left corner of your slide. So feel free to reach out if you have specific questions or questions more about this presentation. But I think that probably wraps up most of our presentation. I think there are some wrap-up slides that are coming our way.
Yes, there indeed are. Excellent. Thank you so much, Leslie and Justin. Great presentation, tons of information, and wow, lots of questions. So I do encourage everyone, reach out to Ohio EPA, ask your questions and get some responses. I would like to just take a moment to thank our sponsors of the Ohio Stormwater Association. We have varying levels of sponsorship from platinum to gold to silver. And there are opportunities if you would like to sponsor our organization. We would greatly appreciate your assistance and contribution. If you're interested in getting involved in any of our committees or interested in participating more in the Ohio Stormwater Association, here's contact information to reach out to us. And we will have additional upcoming OSWA events. Stay tuned. You're on our mailing list. And thank you so much for joining us today. Have a great rest of your day.
Thank you.
Thank you.
Thank you.
Thank you.